now we are ready to discuss the last part of this section, and it's about the fundamental theorem for line integrals. Before we go over this theorem, let's recall the fundamental theorem for calculus. So fundamental theorem of calculus says, okay, if you have a definite integral that goes from a to b of f prime x dx, so here f prime denotes the derivative of f with respect to the x variable, then the value of this definite integral equals to your function value at the right endpoint minus the function value at the left endpoint. So here if this is your x-axis, your x goes from a to b, and this is the function value at b, and this is the function value at a. Now the fundamental theorem for line integrals says the same thing, but it's more general version than the fundamental theorem for calculus. Let's state this theorem. So we have a curve, let C be a smooth curve that is parameterized by the vector function c of t for t values that are in between a and b. Let's define the vector function. Let a vector field, let f of t be a conservative vector field with a scalar function little f. So in other words, the value of this vector field f equals to gradient of little f. Okay. So that is our vector field f equals to gradient of little f. And then the value of this line integral f dot ds over the curve C equals to function value at the endpoint, minus the function value at the initial point of the curve. Now if I draw a picture, so we have a curve C of t. So we have a curve like this. This is my C of t. And if t equals 0, let's say this point is the initial point. Let's say this is t equals a, and the terminal point corresponds to t equals b. It's a terminal point. So using this theorem, we can evaluate a line integral of a vector field very easily. But in order to use this theorem, first of all, your vector field must be a conservative one. This vector field must be a conservative one, and then you should know what this little f is. If it is a conservative vector field, then we can always find this little f using the technique that we showed earlier. Okay. Let's consider a very simple example. Okay. Let's say we are given a vector field f that equals to y cubed plus 2x comma 3xy squared, and in this problem we are given the corresponding scalar function little f, which equals to xy cubed plus x squared. So in other words, if you calculate the gradient of this function, it should be equal to the given vector field f. Now we have a parametric curve c of t that is defined using this parameterization, and our goal is to calculate this line integral using the fundamental theorem for line integrals. Okay, so let's apply this theorem. Fundamental theorem for line integral says the value of this line integral equals to function value at the end point or final point minus function value at the initial point. Okay, now we know what little f is. Little f equals to xy cubed plus x squared. Okay, now we want the coordinate of the initial point and the coordinate of the terminal point. So let's figure out those two things. Initial point corresponds to t equals 0. So t equals 0. Now if you substitute t equals 0 into this parameterization, you will get, so c of 0 get, now t equals 0, so this should be 0 and 0. And terminal point or end point is given when t value equals to 1. So c of 1 equals to 1 comma 2. Great. So now the value of this line integral equals to function value at 1 comma 2, that's the terminal point, minus the initial point 0 comma 0. But what is your f? Your f is this. So x coordinate is 1, y coordinate is 2. So you should get 1 times 2 cubed plus 1 squared. This is the function value at the terminal point, minus, if you evaluate your function at the initial point, you will get 0. So basically this value equals to 2 cube is 8, 8 plus 1 is 9. Now this is the way we used fundamental theorem for line integrals to calculate a line integral. Again, in order to use this theorem, your vector field f must be a conservative one. If it is conservative, then we can find this little f, and using this little f we can calculate the value of this line integral. Now of course you could use the technique that we developed in chapter 13.2 to evaluate this line integral.